The stage is yours.
Thank you very much. So about 2 weeks ago, I hadn't started writing my talk yet, and I had a nightmare about JFocus, that you all started booing and walking out. And I made the mistake of tweeting about the nightmare. People said, oh, that's terrible, but it was just a dream. So I think you've got to do something really bad for Swedes to boo and walk out. So I don't know what that is, but I don't want to do that. Okay. It's easy to get Canadians to boo, but Swedes I think would be hard. So I'm talking about phaser and StampedLock. Just a very brief introduction. I'm from South Africa originally, and now live in Chania, or as you call it in Swedish, Chania. This is the only country where I don't have to say where that is. As I said, I'm from Cape Town. I studied at the University of Cape Town there, and I publish the Java Specialists newsletter. And in that, I do a lot of research. Somebody asked me yesterday, how much percentage of the time do you actually work, and how much do I play around? And actually, I try to do it like 4-to-1 in order to give me lots of time to learn new things. And so from that, the Java Specialist newsletter comes, from the research and trying out different ideas. Also Java Champion, also we're doing a concurrency specialist course here in March. So if you want to know more about concurrency, this is what we're going to talk about more. So often introduce myself, and the only thing people ever ask me is, why the hell do you live on Crete? They don't care about my courses and my consulting and that. This is why. That's my office. Any other questions? No? Okay. So when I proposed this talk, StampedLock had just been released, and so I thought I'd split the talk evenly between phaser and StampedLock. There's a lot to say about phaser, but as I went through the talk with Kirk, as in preparation, we realized that StampedLock is a lot more interesting than phaser. So we'll just spend a few minutes on phaser to go over what you can do with it. Phaser is a Java 7 class, and we need it because we sometimes have to coordinate between different threads. So if we've got threads that have to meet at some point and exchange information at a certain time, then phaser can be used for that. And there are also other possibilities that you can use. The idea with synchronizers is that we encapsulate the state so that somehow the threads know whether they need to continue or stop. And we've got methods for manipulating the state and ways to efficiently change state of the various threads. Now, a very well-known synchronizer is called CountDownLatch. This is a very easy one. You can see the animation here. Basically, I've got 4 threads which are waiting to pass through the CountDownLatch. They've all called await. And when I call countdown, then once my countdown reaches 0, then I pass through. And then after that, the latch is open and we can all pass through. So once we reach 0, it's open. And there's no way to reset it and to start again. So it's really a one-use class. And really the interface is what you see at the top there, await, countdown, and await with a timeout, and that's it. So if you want to do anything more complicated than that, with this particular class, you have to write the code yourself. And of course, that is inconvenient. So the phaser is a Java 7 class, and what it does is it mixes the CountDownLatch functionality, which is a once-off CountDownLatch, and the CyclicBarrier, which allows you to have lots of different cycles and rendezvous at a certain point, a bit like meeting for lunch every Sunday with the whole family. That would be a CyclicBarrier. But the difference with the phaser is that the number of parties can vary over time. With the CyclicBarrier, you have to decide up front how many are going to meet, and if one of them doesn't meet and they don't coordinate in time, then the barrier is broken and you have to reset it. And also with CountDownLatch, it's also a fixed number, and once you reach that number, that's it. You can't reuse it. You can't reset it back to 0. And another thing which is quite nice with the phaser is that it's compatible with fork join. In fact, it's the only synchronizer that you can use with fork join. And with fork join, fork join allows you to specify the parallelism of the fork join thread pool when you construct it. By default, it's according to the number of cores in your system. And what the fork join framework will do is it will try and keep the number of active threads equal to the parallelism, which means you might actually end up with hundreds or thousands of threads if you use if your threads get to blocking state. And the only one that can actually maintain that parallelism is the phaser. Right? So that's just something. I'm not going to show you slides for that, but I will post those slides that are missing here. So the interface here is you construct the phaser. You can construct it with the parent if you want to, with a number of parties, and then you can add parties dynamically, so you can register new parties. You can also have a whole bunch of parties registered at the same time. You can't deregister a lot of parties at once, so that's a missing method. And then you can signal and you can arrive. So if a thread says I've arrived at this rendezvous point, you can call arrive. You can call arrive and deregister. Arrive and deregister will decrease the number of parties by 1. And I'll show you examples where this could be used. And then we've got await advance. Await advance is waiting for a particular phase. And what it does with these methods, the wait method, is it saves the interrupt until later. And that's quite a common thing that we want to do when we catch an interrupted exception, is that we actually want to save it until later. And then the last one is arrive and await advance. This signals that you've arrived, and it also saves interrupt for later. There's another method which you might want to, if you have an action that you want to have at each cycle or at each phase, that's where the name comes from, as you go through different phases, then you can override the onAdvance method, and that then gives you the opportunity to execute an action whenever you reach that particular point. Okay? And there are a bunch of other methods which I've left out, which are for managing the life cycle if you want to. Now, the one example which I found quite compelling is where we want to coordinate a bunch of threads to start round about at the same time. Of course, you can't really guarantee that, because even if you tell a thread to start, you still have to wait for the operating system to actually schedule the thread and to give time to the thread to run. And so I'm going to show you, first of all, the code using the CountDownLatch, and then I'll show you the same code but using the phaser. And you'll see that the code actually becomes simpler. And I like things which are more easy to use. I'll burn your brains in a moment with the StampedLock idioms. So in this method, I start up. I first have to find out how many jobs are there, how many. I get it from the task.size, and I make a CountDownLatch of size plus of the task size plus 1. So I know up front I've got 10 threads, so I make a CountDownLatch of 11. And then inside each thread, I call latch.countdown, and then I call latch.await. And then the threads will all wait there until the others have all started up. And then at the end of this, I'm going to say latch.countdown, and that will be the final countdown for them all to start. And as a result, they'll all get activated at round about the same time. Now, this code is a bit ugly. First of all, we have to know up front how many permits we need. We also have to worry about the interrupted exception. And really, the way I've done it here, by just catching it and ignoring it, is not really the most ideal way of doing things. And I have to call 2 methods, countdown and await. So another approach of doing the interruption handling, this is now the same run method, but written slightly differently, is to first call countdown, then to have a local variable for remembering the interrupted status. So we say was interrupted equals false initially, because we initially assume we're not interrupted. We then try and wait. And if we get an exception, then we save that for later. But we don't re-interrupt the thread at that point. We just go back into the wait state. It's a very common idiom. These are, again, idioms that is used all over the JDK. So we wait. If we do not get interrupted, then we break out of the while loop. Okay? Now, once we exit the while loop, We check whether or not we were interrupted. If we were interrupted, then we reinterrupt the current thread, and we continue by calling the task.run. So there's a lot of work that we have to do as coders to get the interrupted exceptions managed properly. And whereas phaser is a lot easier. With phaser, up front, I specify a phase of 1. That's the current thread that needs to be registered as well. And then whenever I go into the next task, I register another party, so I can change it dynamically. I don't have to know up front how many there are. And then inside the thread, all I say is arrive and await advance. And it does all of this other stuff here for us. So we don't have to do that ourselves. And then at the end, what we do is we call arrive and deregister. This then decreases the count, and then the phasers, the threads can use the phaser as well as a counter if they want to. So this simplifies our code, and there are lots of other use cases for it, and I will actually upload those as a PDF when we at the end of the talk. CountDownLatch we use if we know the count and we want it to be a once-off usage, where CyclicBarrier gets reset. Phaser is more flexible. It's a Java 7 class we can use for doing this type of semantics, but with less code and better interrupt management. So, which brings us to the stamped lock. And the stamped lock is really brand new. I mean, this is, the one that I'm using was basically, it's on the way to be included inside Java 8. It will probably be in the next build or the one after the next build. If you want to see it, you can download it from Doug Lee's website. It's JSR 166. And the reason why we need this is that sometimes we need a type of read-write-lock. And the reentrant read-write-lock is an incredibly poorly performing class. And so what they did was they rewrote this as with a completely different mechanism to give us the opportunity to do optimistic reading instead of having always to do pessimistic locking for the read. And so the stamped lock is highly performant, and I'll show you some performance results at the end of this talk. But the idioms are sometimes a lot more complicated to use. So if you like writing fast code, and you're writing code which is performance critical, then this is something you might want to look at. But it is more difficult to use and to code because idioms are more complicated. So with a stamped lock, you can have optimistic reading. You can also have pessimistic reading if you want to. And you can have writing as well, write locks or exclusive locks, which will always be pessimistic. Pessimistic says we always get the lock and exclude everybody else. Just a very, very brief read-write-lock refresher. With read-write-lock, you've got two methods, write-lock and read-lock, which give you two different locks. With the write-lock, you've got an exclusive lock where no other thread can get in there at the same time. Whereas with read-lock, you can allow lots of threads to come in at the same time. And so if you have mostly reads happening, then obviously this read-write-lock makes a lot of sense because you can have better throughput with allowing more threads using it at the same time. But the read-write-lock interface assumes that both locks are pessimistic, which means you have to wait for you to actually get them before you can continue. You can't assume that you've got them and carry on working. Here's my bank account. Well, it's not really my bank account, but just imagine. And I've got a read-write-lock inside. Inside there's a balance. Now, I've got a deposit method. Deposit, of course, changes the amount in my account. And if I want to modify, I'm actually doing a read, modify, write, then I need to have an exclusive lock around that. So I'm saying lock.write, lock.lock, and then the typical code idiom for using these locks is to have a try, update the balance, and then finally unlock again. And you can see here that I'm not actually storing the write lock anywhere. all the read lock, I call the method, and then that gives it back immediately, and I call lock and unlock on those. So that's a common idiom that we'd use for write lock. And then get balance gets a read lock, and then returns a balance. Now, the problem with read lock is that the cost overhead of acquiring read locks and managing read locks is so high that you need really to do a lot of work for this to be worthwhile. And the guideline is you need about 2,000 code instructions to benefit from the read lock, from the throughput. And I'll show you some graphs later on that demonstrate very nicely this problem that we have with ReadWriteLock. Now, when they wrote reentrant ReadWriteLock, so this is the implementation we had in the past, the only one we had in the past, they would give, in Java 5, read as priority, which meant that if you've got a reader and a writer waiting, the reader would always get them in first. And I'll demonstrate to you how this can have an effect. And when in Java 6, they recognized the problem with this because it would lead to writer starvation, and they gave the writers priority, which meant we ended up getting reader starvation. And I've got a newsletter on this if you want to have a look, 165, javaspecialist.eu, and there I describe this a bit more. Now, I've got to just quickly do a little magic here so I can see what's going on. That's not right. All right. So this is Java 5, the way that ReadWriteLock worked. And you can see here, this is now Victor Grazi's animation. You can see that I've got a bunch of read locks coming in. These are all concurrently being granted. I then ask for a write lock, but I can now issue more read locks whilst the write lock is waiting to enter. And the read locks are just staying in they keep on holding their locks. And because they're not letting go, the write lock can't get an exclusive lock and cannot enter. And so you could get some really nasty writer starvation with the reentrant read-write lock, until eventually all the readers exited and that poor write lock could finally get in. Okay? So this was the problem we had with Java 5. Java 6 came along, and they solved the problem, sort of, by not allowing read locks to come in after a write lock has been asked for. So here I've got 3 read locks, and a write lock has been asked for. Now, when additional read locks come, they have to wait until that write lock has been serviced. And only once they've been serviced can the new read locks come in. So you can see now the write lock comes in, and then once that's been serviced, the 3 read locks come in together. Okay? It's a very nice animation of what's going on. So this is where we come to stamped lock. And stamped lock has much better performance than reentrant read-write lock, and I'll show you some examples of that, some graphs that prove that. The first version that I saw was around about October last year, or beginning of November, and that class had serious starvation on the writers. All right? But that's been fixed. Now the latest version is really fast. The problem is that the idioms are really difficult to get right. And so you need to pay very careful attention when we do that. So if you code it, you don't make mistakes. And even a small difference, even if you stay for 1 nanosecond longer, within the optimistic section, you can impact on your performance. The way that the interface looks is like this. We first of all have got the write section and then the read section. And you can see that in the stamped lock, all of the write methods are all directly written inside the stamped lock. So it's not like with the read-write lock where you first get a lock and then you use the lock. This has got all the methods built in. And the way that it works is that it gives back a stamp. So when I call write lock, it gives me back a number which I can use to determine or to unlock and to manage this lock. So these are all methods for managing the write locks, exclusive locks, and these are always pessimistic locks as well. The number that we get back tells us whether or not we got the lock, and a value of 0 means we did not get the lock. And so, for example, if you look at the method try-write-lock, the try-write-lock would give back 0 if it cannot give you an exclusive lock. Whereas in the other lock, it would just be Boolean. We can also lock with a timeout. We can unlock the write, and we can try and unlock the write. We can also get a normal Java 5 lock back as a write lock. So we can use the old interface if we want to, if we don't want to use this new interface. So we can say StampedLock.asWriteLock, and then use that with the old idioms. And we can also convert to write lock. Now this is quite significant because this is something you could not do with ReadWriteLock. And I'll get back to that in a moment. We also have reading. So this is not a pessimistic reading. This looks very similar to the writing. ReadLock returns a long again, and then we can try and unlock as well and convert our existing lock to ReadLock. So we can take a write lock, convert it to ReadLock. But this looks very, very similar to the writing. It's because they're both pessimistic. It's basically the same interface, copy and pasted, write, converted to read. And I'll show you the optic reads in a moment. First, we need to look at how this works. So here's my bank account with a stamped lock. And see, the idiom has changed slightly. You can see that I've now got a stamped lock inside instead of a read-write lock. And in the deposit method, I first get the stamp for the write lock. I then update the balance, and I unlock the write lock, passing in the stamp. Okay? Now, actually locking the stamped lock is a lot cheaper than locking the reentrant read-write lock. So you're going to get performance gains by doing this. And then get balance gets a read lock. This is now a pessimistic read lock, and returns a balance and finally unlocks the read lock again. And now we need to take a step back, because the question is, why the hell are we doing this? We don't even need to do this, because we could have just written the following. We could have just made the balance volatile, made a synchronized deposit method, which is a pessimistic write lock, and then have the get balance just return the balance value. And because balance is volatile, it'll work. Now, this is much easier than this other code that we had before. I mean, you know, this is a lot more complicated than just having synchronized and volatile. And this will work, but only if you don't have any invariance across the fields. So if you've got a single field in your class, you can go with the volatile/synchronized approach. But as soon as you've got more than one field, and these fields are somehow related to each other, you can no longer do this. For example, let's say you also had a currency in the bank account. So now you've got a currency and a balance. That's actually quite important, because if I change my 1,000 Swedish kronas down to euros, I mean, I don't mind if they keep the probably. I also want them to change a symbol at the same time, and not have 1,000. Actually, 1,000 euros would be good, but 120 kronas wouldn't be good afterwards, or whatever the exchange rate is nowadays. So, and so whenever you've got two fields which are somehow related within the same object, you need to update them at the same time. And this is why you need to have this ability of a stamped lock. And it's something which we weren't able to do in the past. So now the reason why we need to have volatile here, for those of you who have forgotten the reasons, there are two reasons. The first reason is that you need to do it for visibility purposes, because otherwise, if it's not volatile, then the thread is allowed to cache the value locally, and you might never see the update. So you might change it, but the other thread which has been looking at it in the past will never see the update. Okay, so that's one possibility. Because it's a double, it's actually more serious, because the double is allowed to be written as two operations. So if I say write $1,000, it could actually write it as two parts of the 64-bit number. And whereas if I make it volatile, then it's not allowed to do that anymore. It has to write it atomically. But anyway, this will only work in a case where we've got a single field. Over here I've got a point class. Now the point class has got two fields, x and y. There is a relationship between these two points. If I move to somewhere else, those points need to be updated together. And so the first idiom is where we're using a WriteLock to update this. And so you can see here that I've got the move method, and I'm passing in the delta for the x and the y. I get an exclusive lock by saying WriteLock, so no one else can use this at the same time. I then say x plus equals delta x and y plus equals delta y, and then I unlock the write stamp again. So this is going to be similar in terms of execution, or in terms of logic, as making it synchronized, or using a Java 5 lock. Let's look at a slightly more complicated idiom. And this one is doing a conditional state change. Now we're going to step through this together. If I want to do a conditional state change, which means I first have to get an optimistic read to see what the value is, and if it's the correct value, then I can change it. So the first thing I do is to get we're doing a pessimistic read lock. Sorry, what we're doing here is we're doing upgrade from a read lock to write lock, which you can't do with normal read write lock. So what we do is we get the read lock, and we then say, if the state is not the expected state. Now I can see there's a while loop there, but the while loop will only ever execute at most 2 times. So it's not going to be an infinite loop, trying and trying and trying and trying. What we're going to do is we're going to try and upgrade the read lock to a write lock. If you try that with the reentrant read write lock, it'll just hang. It'll never ever complete. We're going to try and do it. If we're successful, then we're going to do the write. Otherwise, we're going to unlock and try again. So you can see here, the while is going to only be executed twice. The first time, I'm checking that the state is the expected state. So while state 1 equals old state 1 and state 2 equals old state 2. And then what I do is I try and convert my current lock to a write lock. So if I'm stepping through this now, at the moment I still have a read lock, and I'll try and convert that to write lock, and I might be lucky, it might actually work. It won't work if another thread also has a pessimistic read lock, or if another thread has a pessimistic write lock, then it will not allow to be upgraded. And so if the write stamp is 0, that means I wasn't successful. It didn't actually manage to upgrade it. And what I then do is if it's not equal to 0, yeah, not equal to 0. Sorry, if it's not equal to 0, then I was successful. And what I then do is I remember that stamp, that write stamp is my new stamp, and I change the state. Okay? And I break out from the while loop, and I then do the unlock and continue. But otherwise, if I didn't have success, in other words, if write stamp equals 0, then I unlock the read, and I get an exclusive lock. I get the write lock. So I say sl.writeLock. We try again, basically. And now we go back to the while loop. And of course, what could have happened is that in the meantime, the state might have changed, because somebody else might have, in between my unlock read and my write lock, might have actually gone and modified the state in between those two. And if the state is not the expected state, we exit again. If it is still correct, what I do is I again call try convert to write lock. Because I now hold a write lock, it's going to simply return the current stamp. And then I'm guaranteed to be able to do the update and exit. Okay? So let's just see how this would apply to our point. Now, our point at the moment is I've got a synchronized void move here, and it's, as I said, because these two are related, I want to actually use a stamped lock. So a stamped lock over here, stamped lock, and I want to wrap this with a stamped lock. Now, I don't have the idioms define an IntelliJ at the moment. I think that's something which they should add at some point. But it's going to be something like this. Long stamp equals SL dot WriteLock, try, finally, SL dot unlock write stamp. Right? That's pretty easy. And let's do the distance from origin, and let's take away the synchronize as well, because we want to have it synchronized as well, otherwise you have double trouble. On this one, distance from origin. So what you want to do is you want to, first of all, get the read lock. So we're going to again say long stamp equals SL dot read lock. Then the try. And finally, we're going to say SL.unlock. Now, I don't know if you noticed this, but it wasn't an unlock write or an unlock read, because you actually don't know what it's going to be. It could be a read or a write. And so we just say unlock and put stamp in here. Okay? Then what we do is inside here we say the following. We say this. Oh, I'm actually looking at the wrong code. Okay, sorry. Just move this down here quickly, and this down here. So we actually want to do this move if at. Right, there we go. So what we do is, instead of having an if, we make a while here. While the state is true. And now we try and upgrade this to a write lock. So a write stamp equals SL dot try convert to write lock, the old stamp. If write stamp is not equal to naught, that means we had success. That means we can now modify these two. Else, we need to unlock the write lock, which will be SL.unlockWrite, the stamp, and we need to get a read lock, a pessimistic read lock now. Sorry, unlock read, and say get a pessimistic write lock now by saying stamp equals SL.write lock. You can see this is not the easiest thing in the world. I don't even know if I got this completely right. I think it's correct. A stamp, a write stamp meets be stamp equals write stamp, right? And a break, do we need a break? Break should be here. There should be the break. So before, it was really easy to use the lock and the lock finally. I mean, even lock finally people got wrong, right? This one is, it's a lot more complicated to get right. Okay, let's see if how this compares to my. Is there anything else? All right, so this I think is pretty similar to what we did. Well, let's get the read lock. All right, any questions with this before we move on? Yes.
You're doing all the same. So maybe in Java 8 with this lambdas, it could be just packaged into one lambda, which gets the if statement, the action, and do it all in the library.
Yeah, it sounds like a good idea. So putting lambdas into that. But one thing I would be slightly concerned about with that is we have to make sure that the performance doesn't get impacted on it, because this type of code is typically very performance sensitive. You know, if you're holding a lock for too long, if you're constructing objects whilst you're, for example, in a critical section, you're increasing your exclusive wait time, which is not so good for performance. But from a readability and coding perspective, you're absolutely right. In fact, from a readability perspective, just make everything synchronized and you're done. Okay. Yes, certainly.
Don't you compare X and old X and Y twice? Do you need that?
Yes, you have to. Because
in case you don't get the...
okay, why do you have to? Okay, first of all, right now, I actually wrote. So this is the idiom which is currently in the Java docs. I tried different ways of writing it to avoid something like that, for example, to avoid having to check X and Y twice.
After lock read, it could get modified by another thread.
Right. So, but what I wanted to say is, if you can think of better idioms for this, they're absolutely very happy to add them to the, you know, as sort of as the body of knowledge grows. Because if you saw the idioms for optimistic read, which I'll show you in a moment, in the past, and the new one's much easier to understand than the old one, and it's also faster. So if you come up with better idioms, please send them to me, and I'll pass them on to the right people. But just make sure that it's also correct. That is fairly important. It's also correct. Lambdas are great, yeah. We should get this integrated with lambdas. Any other questions of this before we move on? All right. So, optimistics. Now, with optimistics, we've got a method called try-optimistic read, which returns a long. And then another method which is called validate. And what validate does is it validates that no exclusive lock has been granted since the call to try optimistic read. All right? It doesn't actually check whether there's been a write, because it doesn't know if there's been a write. It just knows whether it's granted an exclusive lock. And if it's granted an exclusive lock, it has to assume that it's actually been overwritten. So we try to get optimistic read lock. You might get 0 back if you can't get it, if it's being held by somebody else. And what we then do is we check whether the write lock has been issued. If we have, then we have to basically abandon that. Now, this is something we actually weren't able to do very easily with Java. There were some hacks that were floating around. But basically, as soon as you've got two fields, two variables, which in this case is a sequence number and the object which we're protecting, you actually have to have an explicit load fence. And they've added that now to the language somewhere, which location will remain undisclosed. And this allows them to write a stamped lock in order to do this. Now, this is the idiom that we've come up with now at the moment for optimistic read. That's currently the most preferred one. And also what we've determined to be the fastest one at the moment. But as I said, if you come up with better ones, please let us know. Now here's the optimistic read method, and we're going to step through it again. What I do is I do a try optimistic read, get the stamp, and I then read the state into my local variables. And you can see here that the time taken in between try optimistic read and validate is really as quick as possible. You want to make this to be really fast. So don't do a database call in the middle of that try optimistic read, because you're never going to have success, or very seldomly will have success. Which means you always have to go to pessimistic again. So you can see here, if not sl.validate, so if we don't actually get the optimistic lock, if we weren't successful, pessimistic write lock has been granted, so an exclusive lock has been granted, then we basically default down to a read lock. So we say, stamp equals SL.ReadLock, and we update, we read the state a second time, and then we unlock the read. And then we can use the data. So the way that you would do this with distance from origin, you'd say long stamp equals SL.try convert to try optimistic read. And then after just say if not SL.validate stamp, we get the read lock, which is simply stamp equals SL.readLock. Try, and we do this read a second time. Need a semicolon there. Finally, SL.unlock read we can do with the stamp. And that's it. So this idiom, as you can see, is a lot easier to understand. But if you look in the original stamped lock, the idioms there were absolutely horrendous to understand. This one, I think, is more safe, but also performs really well. So I think that was pretty much it. Yes, that's right. Okay, now let's look at performance. We've got another few minutes for that. And I did some research in 2008 when I was looking at ReadWriteLock, and discovered some really bad starvation of writers in Java 5 and relatively bad starvation of readers in Java 6 and onwards. So Java 6 is Java 6 onwards, so Java 7, Java 8, etc. And there's a link, I posted that already. Now, in October, the stamped lock was released, and the writer starvation was absolutely terrible. There was a bug in there. What would happen is that the threads would get stalled and wouldn't activate for like 1 million clock cycles. So you can imagine the starvation was absolutely dreadful. And they fixed that, fortunately. And there was also a bug in there in that they had missed signals. And this meant that you could have deadlocks in the stamped lock. Now, I've not detected any deadlocks in the new version. It doesn't mean there aren't any. So user discretion is advised. Also, with the latest versions from the 28th of January, so it's like last week, they've changed now to have an explicit call to load fence. Writers don't get starved anymore, and also it seems to work correctly. So I ran this on my website. My website doesn't get used very much. It's got 8 cores, and it's completely over-spec'd for what I'm doing. I need to get to Gelastic or something like that. But I use it for performance testing as well. So what I'm saying is that my website wouldn't have had an impact on the results. That's what I'm saying. It's an 8-core machine and running Ubuntu 9.1, 64-bit, bunch of other specs if you're interested. And what I've found interesting is that in most cases, we had a very small percentage of reads having to be converted to pessimistic reads. So my experiment, it's very similar to the one I had in my newsletter. There were always less than 10%. In fact, there was only one time where it was even close to 10%. And most of the time it was like 0.1, 0.3%, 0.5%. That it was converted from that it needed to be converted from an optimistic read to a pessimistic read. So this meant that most of the time optimistic reads worked. And so what this shows, it shows you how much faster the stamped lock is than the read-write lock, the re-entrant read-write lock. You can see with a single thread, I've got, the bottom of the graph, it's a little bit complicated. R equals 1 means there's 1 reader and 0 writers. And R equals 0, W equals 1 means there's 0 readers and 1 writer. So you can see that the readers were quite a bit faster than the re-entrant read-write lock. But for the writers, they were almost the same speed. It's sort of what you would expect to see. There's a small increase, but not enough to really make going over worthwhile. Here with 4 threads, you can see that now that the numbers are quite different. You can see with 4 reader threads, we're 64 times faster than the re-entrant read-write lock. That's quite significant. And down to 11 and 12, and then 353 times faster. I'll get back to that in a moment. You can also see that the write lock for, if you have one write lock and 3 read locks, was very slightly slower with the stamped lock. And this proves that my results are correct. If I only show you something that's faster, that can't be true. So here you can see another graph. Here you can see with 16 threads. Now you can see this outlier on the right-hand side, where it's like over 1,000 times faster. That is because of the bug that we had in the re-entered read-write lock. That's the proof that there was a bug with starvation. Okay? But you can see that we get really good speed ups. I mean, it's like almost it's like 80 times faster on the left-hand side for the reading. Okay, the reader throughput. You can see here, this is a logarithmic scale, how as my threads increase, my throughput goes up on the reading. And I've got 8 cores, and so it levels off at 8 cores, which is, again, what you'd expect to see, the results you'd expect to see. With the writers, if you've got a single thread, it's a trivial example. So with a single thread, it actually performs really well. In fact, almost too well. There's no conflict at all. But as soon as you've got 2 threads, then the conflict enters in, and you have this big dip down, and then it comes up again as the number of writer threads increases. Here you can see the mixed reader throughput with stamped lock. This is basically, you can see the number of reader threads is decreasing, and so the throughput goes down. And at the same time as the readers are decreasing, the writers are increasing. So this is the graph of the stamped lock, and with the read-write lock, re-entered read-write lock, you can see the throughput graph. It's the same thing. Also, you can see the volume. Here you can go. It's like 2,000, 3,000 times. It's 3,000 the throughput, versus here it's like in the 30s, 40s. So there's a really big difference in terms of throughput. And again, you see the rightmost graph, where you have a lot of writers and only one reader. The writers starve out the readers, and that's again the starvation problem we have in re-entered read-write lock. So the conclusion is, in our tests, this performed really well, much faster than re-entrant read-write lock, gives you a way to do optimistic locking. And your idioms are really important. First of all, you need to make sure that they are correct. If they're not correct, you've got a problem. And also, even a slight change in the idiom or a slight change in your code can have a big impact on performance. For example, what I did was in one of my tests yesterday, I changed it so that I tried 3 times to do optimistic read. And if I couldn't get it 3 times, then I defaulted to pessimistic. And it sometimes made it faster, sometimes smaller. So that's where performance tuning comes in. If you're interested in discussing this, please also post on JSR 166 mailing list. Just Google that, you'll find it. If you have not subscribed to my newsletter, please, if you want to, do so. And remember, we're doing a full 4-day concurrency course here in March. So thank you very much. Any questions? Got 1 minute. One question from Kirk.
Slide 52. You go back to slide 52.
Slide 42, sorry.
52.
52, okay.
There's a nice effect here.
Okay.
51, 2.
I'm trying to count to 52.
There you go. Right. So it seems to me like with more threads running, you should have more interference, which means the graph looks backwards to what you'd expected.
It does, yes.
Can you comment on that?
No, you can comment on that, because we spoke about this before, so so you can comment on it.
You can comment on it.
No, you can comment on it.
It's an interesting point, I think, it's that there's a communication overhead that doesn't get amortized out until you start going to higher thread counts. And so at 2, you're not amortizing it. So there's like a fixed cost and a variable cost, and the fixed cost is being hit on 2 core, but on 4 and 8 it levels out.
Now, what we also suspect is that if you have more cores in the machine, that you can see that 4 and 8 is sort of on the same level. And probably, but this is subject of investigation, probably if you say you have a 32 core machine, it'll probably stay level up to 32 and then go up.
Or multi-socket would probably.
Or multi-socket, yeah. Lots of possible results here.
More questions?
Yes?
You mentioned you had to do about 2,000 instructions when you use the reentrant ReadWriteLock for it to pay off. What is the... How many instructions do you need with a StampedLock?
Oh, that's a good question. I think 1. Because it's optimistic. So if you're doing optimistic reads, you'll get very good performance with that. So with reentrant lock, you can see from the graphs that you have to really push it to get improvement. Whereas with the stamp lock, you're immediately there.
Okay. Thank you very much.
Thank you very much.